Yay, quadrilateral time. Okay, you might be watching this in class. Please be nice to the sub. All right, this is about quadrilaterals, first thing. All right, first of all, what is quadrilateral and what is a polygon? Polygons, first of all, poly just means not the name of your parrot. Poly is many, and gon means side. For some reason, we don't say trigon, but we could for triangles. Anyway, polygon just means something that has segments connected only at their endpoints to make a closed figure, such as this. This one is what we refer to as convex, whereas this one is what we refer to as non-convex. It's kind of hard to define the term convex, but I think it's easier to just show you a bunch of examples, so let me do another one. Convex stuff. All right, so here's some examples of things that are convex. This term comes up a couple times because it's in the part like the body of a theorem. For convex polygons, blah, 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 and you have to go, oh, what's a convex polygon? Convex polygons is where all the corners kind of point outward. Triangles are always convex. Yeah, outward pointing corners is kind of the best way I can describe it. Whereas non-convex, again, there's a longer technical definition, but this is good enough. Non-convex, it could be a quadrilateral, it could be non-convex, like that. Or like this one up here, or something where you have the corners that are also pointing in. Because we're going to be talking about the angle sum inside a polygon, and life is a lot easier when all the interiors of all the angles are also in the inside of the polygon. Here, the interior of this, well, this is easier to draw on. The interior of this angle here is kind of outside the polygon, so the part that's less than 180. So it makes our rules about angle sums kind of messed up. So convex is where we like to stay for most of these rules during this chapter. Okay. All right, so we name them by the number, by listing the vertices in some sort of consecutive order around the figure. So you could start anywhere you want, but if you're going to call this a quadrilateral by its letters, with triangles we didn't have to worry about this. I could have called this upper triangle here HGE or AGG or GEH, whatever I wanted to. When I name this outer quadrilateral here, if I start at G, I could call it GFEH. I could call, whoops, and I messed up. I could call it GFEH. I could call it GHEF. That's fine. I could call it EFGH. That might be the intended one. But I can't call it FHGE. That is not a valid way to name this quadrilateral. When you see a name of a quadrilateral and not a picture, or any polygon without a picture, you can be assured that these vertices are connected by segments that go around the thing. Again, you can go either way around the polygon, doesn't matter. I could go that way or that way, and I could start at any point. But for this one, I'd have to call it MLKJI or JKLMI. I can't go IL. I can't make a star. ILJMR. Sorry, it's okay. So that's nice. These other segments, if you were going to go along those other weird connections, those dotted lines here, those are called diagonals. That's another term that comes up in the theorems. The diagonals of a polygon do blah, blah, blah. So you have to know what they mean when they say diagonal. Diagonal doesn't mean any sort of, magical street in Harry Potter. It also doesn't mean any particular direction. Diagonal doesn't necessarily mean that direction. Diagonal just means it connects, makes a connection within a polygon that's not already a side. So it usually goes through the middle. Okay. Oh, and by the way, these are not all of the diagonals possibly shown. There's some missing diagonals here, like they didn't draw IL, and they didn't draw IK, and they didn't draw MK. There's a whole bunch that they did, like they didn't draw SP. So they just drew some. Okay, names for things. I think you probably know all these by now. You don't want to watch me type. I'll pause and fill these out just so you can get all the names. I'm kind of sorry they didn't put in one here for 9 or 11 or 12, but this book just, I guess, wants you to know these. Let me pause and fill in these definitions, and I'll be with you in a second. There you go. And what you need to, I guess, remember is that these are all these Greek prefixes, and you probably know most of these already. Yeah, there's a great video we have about nonagons, which is 9, and undecagon, 11. Oh, sorry, the video is about nonagon. I'll show you that when I get back. It's kind of silly. Yeah, triangle and quadrilateral kind of don't follow the pattern of agon on all the rest of them. In general, when you get to n sides and you don't know how many sides a thing has, and we have a lot of problems where we just want to start with a generic polygon of unknown number of sides, we refer to that as an n-gon, and then we can solve for n. If I was there, or if you had a chance, oh, just wait a second. I just realized I could do this on Sketchpad. You knew this about triangles. Triangles, no matter what the triangle looks like, you know that the angles add up to 180. Now we're going to expand that. Here's something I just made in Sketchpad. Here's a random quadrilateral, and I measured all the angles, and those are changing up here as I measure the angles. And then I made it do a calculation of, well, what's the sum of all those angles? And notice no matter what I do with this thing, until I start doing that kind of stuff, remember we talked about non-convex, this is where life gets weird. But as long as we stay convex like this and all these corners point out, notice this sum right here always turns out to be 360. If you really want a proof of that, it's really not that bad. It has to do with this hint right here. Can you tell why they might add up to 360 now? Think about the angles of those triangles. Those triangles have to add up to 180 all the time, and the sum of the angles in those triangles, if we marked them all, they would be exactly all the measures total in this quadrilateral. So they have to add up to 360. And back to this, if you didn't see all this junk in the way, look at the way these are all divided up. Notice there's 2 triangles here. There's got to be 3 triangles in a pentagon. There's got to be 5 triangles in a septagon, or whatever this thing is. Oh yeah, that's not in the list either. 7. Wow, this book's boring. All right. We can figure out, because of the number of triangles, we can figure out how many degrees it has to have total. Let me fill that out. Okay, so because of the number of triangles in each one of these things, a quadrilateral has 2 triangles, and two triangles would be 360. A pentagon would have 3 triangles total worth of angles, so that would be 540, etc. This pattern seems to go pretty well till we get here. I didn't just add 180 going down here because we skipped one, right? Because we skipped from 6 to 8, and we skipped from 8 to 10. I think it might be more valuable if you saw all of them. Anyway, how am I able to do that so fast? Well, or what do we do if, in general, I just have n-gon? Well, oh, sorry that moved there. I don't know if I can fix that quick. Yes, okay. For any for any n-gon of unknown sides, we know how many triangles it must have. It must have n minus 2 triangles that look like this. Notice this thing over here had 7 sides. If I start chopping up into triangles with 7 sides, it's going to have to make 5 triangles. Notice I have to exclude vertices here at T and O. That's kind of how we get the minus 2. Anyway, it's that many triangles, and each triangle is 180. So if you know the number of sides, you can know the sum of the angles on the inside of that figure. And here's the theorem that says so. So it's called polygon interior angle sum. So whenever you use that in a proof, if you ever got this pentagon and they ask you to find angles in here, and the way you do it, kind of like with triangles in 180, you can say pentagons are 540 because of this rule, polygon interior angle sum. And that works for hexagons at 720, and etc., etc. Quadrilaterals at 360. Quadrilaterals at 360 is probably the most common one you're going to use this chapter, because this is mainly a chapter about quadrilaterals. That's interior angles. Those are the angles on the inside. We also talked about exteriors with triangles. Exterior angles at a corner of a polygon, remember, are if you take one of the sides and extend it like a ray, that angle that it forms outside is called exterior. The interesting thing about exteriors, if you took one exterior everywhere, now that's just one, it's not both, but one at every corner, those things, no matter how many sides the thing has, so this has nothing to do with number of sides, hexagon, pentagon, quadrilateral, triangle even makes this true. If you add up one at each corner, it will always add up to 360. The way I like to describe that is, if you were driving a car, and you started out here, and you were driving, and then you made a turn here, the amount of degrees you turned away from the way you were going straight would have been that many degrees. Does that make sense? And you drive along this street and you turn, we're always turning left here. I turned left again, but I turned left by that many degrees, and then I kept going and I turned left by that many degrees. By the time I'm always all the way around and done with this trip and going the same direction I started with, how far have I turned? Well, I've turned 360 degrees. Because I went completely around to the left all the way around till I was going the same direction I started in. And the amount of angles I've turned has been, at every corner I turned another exterior angle till I did all of them once. So that's the way I like to remember that. That's 360, no matter how many sides there All right, well, that's a big font. All right, polygons can be classified as equilateral, equiangular, or regular. Unlike triangles, it is possible to be one of these and not the other. There'll be plenty of examples of that in the book, but you could be, oh, just real quickly, you could be equilateral. Oh, how about a quadrilateral? It's possible for this to happen. Those four sides could be equal, but the angles aren't equal. Likewise with quadrilaterals, it's possible for these four angles to be equal. They could all be right angles, but that is not equilateral. So this is how you could be one or the other. Or regular. Regular means both of those things. Well, as long as I'm in quadrilateral land, let's draw a regular quadrilateral. You probably have a better name for this, but if all of that's true and all of this is true, then it's what we call regular. And it wouldn't be right angles if we're talking about something with more sides, like for a pentagon. That's not bad. If all of these angles are the same, and all of these sides are the same, then we would call that regular. You see regular polygons all the time. All right, so here's part of a 32 gun. I actually made this in Sketchpad. Let's see if I can find it here. Yeah, I made this 32 gun in Sketchpad. Can I show you all the sides? This is crazy. Show all hidden, yeah. So I took this point and I rotated a bunch of times. If I do that right, yeah. That thing has 32 sides. They're all the same. And then I started making exterior angles at each corner so you can kind of see what it looks like. I took the points off here so you can kind of see what one of those corners looks like kind of blown up. The question is, find the sum of all the interiors. The interiors are angles like that. So I need to find out what all those are. Oh wait, this just said it was a polygon. It didn't have to be regular. Doesn't matter. It's going to have the same sum on the inside. And we can do that by applying our favorite formula here. This is just use the n minus 2 times 180 for the interior sum. And here n is 32. So 32 minus 2 times 180 is 30 times 180. Can I do that in my head? Because 18 times 20 is 54, and then I have hundreds of degrees left over. I get 5,400. The sum of all these angles, these add up to 5,400 degrees. It's like the temperature of the sun. Kind of looks like the sun. Okay, bad geometry joke. And then what happens if I add up all of these angles? One there, one there. They're really small, and there's 32 of them. This is interior, remember, 5,400. Exterior angles, doesn't matter how many sides I have, doesn't matter if it's regular or not. The exterior sum is always, always, always 360. Okay. Next, this is regular polygon, so I did this one right. Regular polygon has 12 sides. I call that a dodecagon. Find the measure of each interior angle, so each one of those things. Two ways to do this. You can use the interior angles. I can find out what the sum of all these angles is in here. All the interior angles have to add up to this, which here is going to be 12 minus 2 times 180, that's 10 times 180, that's 1,800. And I know that all of them are the same, so because I know they're all the same, and only because I know they're all the same, I could just divide that by 12, and oh geez, what do I get? Sorry, I'm running out of time. I didn't want you to watch me agonize over that. I get 150 degrees, so each one of those angles is 150. An easier way, I think, is exterior. The sum of all of these exterior angles has to be 360. And think about how many of them there are. There are 12 of them. So each one of those is 30. So if this is 30 right here, that wasn't the question. The question is, what's the measure of an interior angle? Well, the interior angle is right here. If this guy's 30, guess what? That's 150 because they must be supplementary. Wow, this is easier. So I like the exterior angle method better. Pause that and watch that again if that didn't make sense. All right, so the sum of the measures of the interior angles of a polygon are 6 times the sum of the measures of its exterior. Well, so 6 times the exterior equals the interior. Is that what it says? Measures into, yeah. So this is n minus 2 times 180. This is 6 times 360. Let's do some algebra, and we get n equals 14. All right, find this measure here. Well, the only way to attack this, I have all these interior angles measured. I have to go for the sum. So I figure out the angle sum, and pentagons, you'll get used to this pretty fast, is 540. 540 has to equal all of these added up, and I do some algebra, and I get that answer. Sorry, I got about 30 seconds left. All right, the number of sides is unknown here. So I just know that this is 171. I think the easy way to do this is think about, okay, well, what's the exterior there? The exterior there has to be 9 degrees. I know that 360 of them is the sum of all of them. So by simply dividing 360 by 9, I find out how many of them there are. There are 40 of them, so this is a little slice of a giant 40 gun. Okay, see you in class. Be nice to the sub.